Hello and welcome to my course Math by Arrows. This is the first class. My name is Manuel Casasola Merkle and this is my assistant, the Stanford Bunny. In this class, we will discuss the most important and most basic mathematical concept that makes it possible to display stuff inside 3D programs, the vector. And the vector is basically the entity that gave its name to the whole field of mathematics, vector math. So you see, it's very important. So 3D is about creating stuff inside a computer program. What we try to build is a model of the real world. So we try to mimic real shapes, and to do this, we need a concept to translate shapes to numbers, because computers are work with numbers, really live in the world of numbers, and that's why we need numbers to tell the computer what to display and what to do with stuff we build inside 3D. And we are the first who thought about this, but the ancient Greek did. This guy is called Euclid. He is a Greek philosopher. And he dealt a lot with geometry and tried to understand his environment, because he looked around at the stuff around him and understood that most of the shapes surrounding him are made up of very basic building blocks, of very basic shapes. So as an approximation, most shapes can be approximated with basic geometric shapes like these. If you have a look, for example, at these still life paintings here, most of the shapes you see here are basically cylinders, spheres, cubes, etc. Of course, a little bit more complex and with a little bit more detail, but the structure is really not that different to the basic shapes. And that's why the Greek decided to study the basic shapes, because they are a lot easier, of course, and can be measured. So the most basic concept is that of a circle, for example. A circle can be described by a point that's a center point and a distance. If I have a certain distance, let's call it the radius, r, let's say it's 2 units, then I can define the circle as a set of points that are all 2 units away from the center point. A little bit more or less like that. Well, not a circle at all, but you get the concept. That means this number here, this number defines a geometric shape. And by doing so, I'm able to teach a computer to draw a circle by giving it the radius, of course. The problem is this concept is not very versatile, because if I have another form, for example, the square, a radius won't help me much. For a square, I need different information. I need, for example, the 4 corner points. I can specify these and then tell the computer to connect the dots with lines, like I try to draw here. And then the area included or surrounded by these lines is my square. As you can easily see, now I don't have one number as with a circle, but I have 4 points that have to be specified. And you see, the problem is every shape has different parameters that describe the shape. So something more versatile was needed. Fortunately, there was another guy who lived in the 17th century. His name is Descartes, and he's a philosopher too, a French philosopher. And he came up with a great idea, the Cartesian coordinate system. Everybody knows what that is. It's the coordinate system we know from Cinema 4D, we know from school. But this coordinate system is really a great idea, because what that did was Descartes created space axis. And by doing so, he gave a measure to space. So I do it for simplicity in 2D, but you know it all in 3D too. He created 2 axes and measured them. So this is 1 unit, 2 units, 3 units, 1 unit, 2 units, 3 units. And by doing so, every point in the whole space there is got a unique number combination. So that means the most basic geometric shape is now easily transferable to numbers. And the most basic geometric shape is, of course, the point. I draw a point as a little circle, but in fact, the point is an infinitely small little dot without any dimension. It has no dimension at all. So now, with this Cartesian coordinate system, I'm able to specify points in space. I put a point here, and it's clear by traveling 3 units along the x-axis and 3 units along the y-axis that this point has the coordinates 3, 3. Another point could be 1, 1 or 1, 3. By convention, you write the x-coordinate first. And this is really a great system because now I'm able to create as many points as I want and tell the computer to display these points at the right location in space. And this is exactly what makes up the Stanford bunny. Because if I switch to point mode, you see the Stanford bunny is made up of a lot of points that lie on the surface of the bunny. So basically, it's the very same idea as with a circle, but a little bit more complicated. It's not all points have the same distance to a center point, but this surface here is a set, so the group of all points that lie on the surface of the bunny. And with this concept, you can actually describe every form you have in mind. With points, you can describe everything inside a computer with numbers. So basically, if I draw enough dots, I can describe a curve. You can imagine drawing intermediate dots, as many as you like. What I can do is drawing 4 dots and then filling in the gaps with dots to draw a square or a circle. And if I give every dot his coordinates, I can specify this dot with the coordinates x, y, and all the other ones, and tell the computer to display them at the right position. Now that we have points, it's time for something new. It's time for vectors. So what is a vector? A vector is basically an arrow. This little arrow here, this is a vector. This is a geometric interpretation of a vector. And vectors are used to describe a different concept than points because they resemble a displacement. So they are a relative thing. They have a length, as you see here, and they have a direction. And that's why we use arrows to describe them, because arrows have a direction and length too. And these two quantities specify a vector. So basically this vector here has a length, that's this distance here, and it has the direction specified by its tip here, by its head. And vectors are used to describe 3D elements mathematically. But how do points and vectors relate? That's a question we have to answer. So let me draw a coordinate system again. Y-axis and x-axis, and measure these 1, 2, 3, 4, and 1, 2, 3, 4. In this coordinate system, I can specify a point easily. It has the coordinates 4, 4. And this concept means position, location in space. It's an absolute position. This point lives here at the coordinates 4, 4. And with the same numbers, I can describe a vector. The vector that points from the origin to this location in space, this little arrow here. And this is a relative displacement. If you travel along this direction for this distance, you end up here at this point. And this is a relationship between points and vectors. Vectors are used to describe a displacement, And points are used to describe a location in space. The cool thing about vectors is it's a lot easier to deal with them than with points. That means a point is made up of coordinates. It needs two numbers to describe a point. In 3D space, we need three numbers. And if we try to do calculations with points, we have to do calculations in 3 dimensions with three numbers all the time. And that tends to be tedious. And a vector is a lot easier to describe because I can define a symbol. Let's take V for vector and put a little arrow on top to distinguish it from a normal number. So a normal number would be, for example, A. And to indicate that this is a vector, I put a little arrow on top. And now I can talk about these two coordinates with just one symbol. And that makes things a lot easier, especially if we do vector calculations like adding two vectors or subtracting two vectors or multiplying vectors. It really simplifies because instead of writing stuff like, for example, adding 2 points with the coordinates 4, 4 and 2, 8, for example, I now could write add the vector v and the vector w together. And of course, the calculations have to be performed on the individual components of the vector, but that's not important at all because Cinema 4D will deal with all these calculations. What we have to understand is nothing but the concept, the basic concept. And for this, it's sufficient to use one symbol for one vector. So where does this vector live? The answer is a little bit interesting because I drew the vector here starting at the origin and pointing to this point, but basically if I draw this vector here with the same length and the same direction, it's the same vector by definition. And another vector here, same length, same direction, same vector. So vectors are really not located in space. It's a convention to put the vector at the origin and view it as a displacement starting from the origin to this point, and then I can use a vector to describe a point. And that's exactly what Cinema 4D does to specify points. It stores vectors, and these vectors start at the origin and point to some location in space. And this is the location where Cinema 4D draws a point. And this is really useful and simple, basically, once you start to think in arrows and forget about the coordinates. So, back in Cinema 4D, I try to show you how this looks like in Cinema 4D. To do so, I wrote a little Python generator that will visualize the vectors. So if I create some sort of primitive, let's say a platonic object and convert it to polygons, and switch to point mode, you see the points in space, and these are the points we discussed earlier. But what about the vectors? So let's give the platonic display tag so that we can see through. And what you see here is a representation of this object inside of Cinema 4D. These vectors here make up the object. They start at the origin, as I showed you in 2D a minute ago, and point to the individual points of the object. And if I move the object around, what Cinema 4D does is updating the vectors. So basically, this group of vectors specifies the object. We can do it with another, a little bit more complicated object, like a sphere, for example. Same procedure. And you see, all these vectors here make up this sphere. They start at the origin and point to the individual points of the sphere. And this way, they specify the numbers necessary for Cinema 4D to display the point. And how does a vector look in the attribute manager? We can easily create one. We create a user data, call it my vector, and switch to type vector. Here it is, my first vector. This is a vector. It has 3 components because we are in 3D, so we have 3 coordinates. And these 3 components make up, as we know now, a little arrow. And with the points of the sphere, it's not different at all. If we go to the structure manager, what we see here are all the point coordinates. I can click on individual points and they are selected. And you can see these coordinates. And these are the coordinates that specify this point. And what this is a vector. In code, it means these 3 numbers are grouped and are treated as one entity. So you have one index number, 13, and this is a data type vector, and that means these 3 numbers specify a translation, a direction, and a length, and the point we reach when we travel along the vector is the point Cinema 4D draws. So basically, it's a little bit more complicated than one might think at the first place. And now starts the fun stuff, because now I'm discussing different operations we can do with vectors. Now that we know that Cinema 4D internally deals with vectors, we can do calculations with vectors. And the first most important calculation we can do is addition. So now we will talk about vector addition. So what does vector addition mean? Basically, adding 2 vectors. I will show you the algebra, but far more important is the geometric meaning. Nevertheless, to get the concept, I'll show you the algebra. Let's say we have 2 vectors. For vectors to exist, I need a coordinate system. And inside the coordinate system, I have, let's say, the vector 2, 2. This guy here, and then the second vector 1, 2. Take a different color. This is the other guy. Let's call this one B and the other one A. Okay, and what you do if you want to add these 2 vectors is nothing but adding the coordinates. That means 2, 2 plus 1, 2. What does this give? What you do is adding is the individual components. That means what you get is another vector with the components 2 plus 1 is 3 and 2 plus 2 is 4. So this is a result vector 3, 4. Where is this? 3 and 4. So something like this. 3, 4. We have another vector that is here. Okay, great. But I told you earlier, we don't want to deal with coordinates because it gets complicated. What does this mean geometrically? If you add 2 vectors, all you do is take one of them and put its tail to the head of the other. So imagine you take vector A and put it to the head of vector B. Let's do that. I told you vectors are not located in space. I can move them around freely and they don't change. That means I can take this vector as long as the length and the direction stays the same and put it on the head of vector B. So this is vector A2. And these 2 vectors together specify a location because they are a translation. And if I add them, I travel first along vector B to this location, and then along vector A to this location. And I end up at point 3, 4. And the same thing is true if I do it the other way around, because if I write it down, A plus B gives the vector C, but B plus A gives the same vector C. This is really the same law as with standard numbers, where you can switch the individual operands and the result will be the same. So if I take vector A and put the tail of vector B to the tip of vector A, I will reach the exactly same location. And this is a concept you should try to remember. That means it's really easy. Think in arrows. If I have some vector A and some other vector B, to add them, it's really easy. Just take vector B, put it to the head of vector A, and you will get the location of the result. And if you connect the origin of the coordinate system with this location, you have the resulting vector C. And as I told you, it works the other way around too. I can put the vector A to the head of vector B and reach the location vector C in the same way. So that means the two vectors you want to add form a parallelogram, as you can see here. And the diagonal here of this parallelogram is a resulting vector A. And it makes a lot of sense intuitively, if you think about vectors resembling translations, because it's really a chain of translations. The rule says travel along vector A first, then travel along vector B, or the other way around. Okay, I switched to Cinema 4D to show this in Cinema 4D. What I did here is trying to visualize how this looks like in Cinema 4D. And to do so, I need a vector primitive. And Cinema 4D, unfortunately, has no vector primitive. That's why I built one. This Python generator here, you can see it here, and it looks complicated, but it's really easy. What I did is I created a Python generator and gave it custom parameters. Of course, the vector itself, I tried to display. In 3D, I have 3 coordinates making up the vector. And the size really does nothing but making it thicker, so, such that you can see it easily. And what I do inside the code, it's not necessary that you rebuild it, because you can download this scene and have a look on your own if you're interested. But basically what I do is I create a spline with 2 points, and these 2 points, one of them is at the origin and the other one is at the vector, so translated. And then I create a sweep NURBS and a little cone to display the arrow and return both of them inside a container. That's all I do. Okay, so let's take one of these guys and create a new scene and paste it here. That means I can take this vector object and go to the coordinates and move them around. If I put, for example, 100 here, the vector points to a different direction. And I think it makes a lot of sense, because if I put in the coordinates, let's say 100 and then 0 and then 0, I have the vector that goes in x direction, because this is the first component, x, and has a length of exactly 100. And Cinema 4D Space Grid has squares with length 100 units. That means I have this green guy here. If I do it the other way around, let's say x 0 and y 100, I have a green vector pointing up, and that has the length of exactly 1 Cinema 4D square. Okay, and now I want a different vector. And really, I can do all of this inside of Espresso without visualizing the vectors, but I think it's easier to understand what's going on if we see what the vectors do. So let's create another vector, call it B. And this one, for example, should point to this location. It's 50 and 50. It's a little bit shorter. Let's give it a different color. Let's say red. Oh, it's luminance. Or orange. Okay, now I have these 2 vectors, and now I want to add them. I need, of course, a result to display the result of the operation. Call this one C and give it another color too. Let's say blue, like this. Okay, and now I want to do the operation inside of Espresso. That means I create a Cinema 4D Espresso tag on vector C. I created a custom layout for Expresso and code because I do so much code in Expresso that it's easier for me if I have all of this stuff here inside of a new layout. I have the X pool here for all the Expresso nodes, the console, the thinking particle settings, because this is stuff I deal with. I have the script manager and the Expresso editor, and of course a viewport, because it's very important that as long as you work inside of Expresso, you have to have a viewport visible, because Cinema 4D tries to optimize stuff, and that means if no viewport is visible, Expresso won't do any calculation. So don't wonder if you maybe create a new layout with an Expresso editor, but without a viewport, and nothing works. Because without a viewport, Cinema 4D never triggers the Expresso calculation. That's one of the reasons I have a little viewport here. Okay, but now what we need is the vector A, of course, and the vector B as inputs. And maybe I color code them. You can give the nodes colors. And if you click on this color field here, you get a little color chooser, and such that I can pick the colors directly to the same colors. Vector B, I do the same thing. Now I have my inputs color-coded, easily visible. I have vector A and vector B, and now I need the data. And the data is under parameter vector. That's because I defined it to be there. I created a new user data group called parameter, and there I have the vector displaying here. Same thing for vector B, parameter, vector, vector. Okay, now I have my two inputs, and what I have to do now is add them. So let's grab a math node. Here's the math node. No, sorry, it's a float math. Here is a math node. And now what we've learned is that's a different operation to add to normal standard numbers or to add to vectors, because vectors are made up of multiple components, and the operation is of course different because I have to add the individual components, and that's why I have to tell Cinema 4D that these entities are vectors and not normal numbers. So switch to the parameter tab of this math node. To the node tab, and there you have a input menu called data type. And here you have different data types. One of them is real, so a real normal number. In our case, we want to switch to vector because we want to add vectors. And the function the node has to perform is add, as it displays as a standard. They have different operations here, but we need add, and now we can add these two vectors. And at the output, we will have the result. Now I need an object to display the result. I prepared this vector C, as you know. Let's give it a color too. Pick the blue to stay consistent. And now I create a port for parameter vector on the left side and put in the result. And what you now have here is exactly what I drew in 2D. I have a parallelogram of these two vectors. So if you think of this orange vector being translated to the tip of the green one, I form a parallelogram, and the diagonal of this geometric entity is a new vector C, the addition of both. And that's really great, because now that I can add vectors, I can reach location in space by performing multiple translations. So I can chain translations together to reach every location I want to reach. And this is very useful for a lot of things. But we are not done yet. To really understand what's going on, let's try to visualize the concept of moving one of the vectors to the tip of the other. For this, I need, of course, another vector visualization tool. So let's copy one of them and call it A2, just to indicate that's a copy of A. So A2, same concept with the color. Choose screen color and pick this one. It's usually a very good idea to color code all the nodes inside Expresso. I do it a lot because Expresso graphs tend to get convoluted. And with this color coding, they are a lot easier to read. I somehow managed to skip this blue color. Okay, now I have A2. It's the same vector as A, as I have the same numbers here inside this edit field. And what I want to do now is I want to move it to the tip of this vector. And how can I do this? This Python generator here is located at the origin, but of course I can move it around. And what I do now is nothing but move it around by code. That means I create a global position port. And as you know now, the global position of every object is nothing but a vector 2. And put in here, the vector B. And what that gives is the vector A2 moved to the tip of this first vector. And why is this? Because this vector can be seen as a translation. So all I do is translating this whole object to this location. And you see what this gives is this green translated vector points to the resulting addition point between vector A and B. And the same thing holds true, of course, for vector B2. Let's clone this one, put it in here, give it a color code, because it's a copy of B, and now give it global position and move it to the tip of A. And what you see now is, okay, great, this is a parallelogram, and here you have the resulting vector. And this is of course live now. That means if I select both B vectors, and I have to do both at the same time because both rely on the same numbers, and change the number here, say to 300, I get a live updating vector addition display. Or let's say I go to 1, I have this. And the blue vector gives me immediately the result of the addition of the two. I went one step further with this combination here, because what I did here was creating two null objects and giving them an Expresso tag 2. And what this Expresso tag does is really nothing but getting the global position of this null object and feeding it into the vector field of this vector B in this case. So into this field, you can see that this one is wired inside of Expresso because it has this little box here with the triangles in there. So as a side note, basically in Cinema 4D, every parameter that has a circle in front of it is animatable. And once you wire it and anywhere inside of an Expresso tag, this circle changes to a square. And by this you see, okay, the parameter is controlled by Expresso. That's very useful from time to time. Okay, by doing so, by using these null objects, it's interactively now, interactively controllable, because I can move the point around, and what happens is Expresso gives the new vector information to this vector A and does the calculation here on A plus B. I do nothing but adding vectors, add, and the result is fed into this vector A plus B. And this way, I can move the points around and see the result of the addition immediately. Next on the list is vector subtraction, as you might have expected. So now let's talk about the next concept, vector subtraction. What could this mean? Well, vectors, you know by now, can be subtracted given another vector C. So let's say this vector here is a vector 2, 3, 2, minus the vector 4, 1, gives, just subtract the individual components. 3 minus 4 is minus 1, 2 minus 1 is 1. This is a vector C. Okay, but again, What about the geometric meaning of all of this? If I have two vectors, 3 and 1, let's say, this is A, and 4 and 3, this is B. Look at this and try to grasp intuitively what the subtraction could mean. What is a subtraction? A subtraction is really the difference between two things. So if I subtract 7 minus 2, it's 5. So 5 is a difference between 7 and 2. And what could be the difference, geometrically speaking, between vector A and B? Well, I think a good idea could be that this is this vector, because this vector here is a difference between this location and this location. Let's see what the numbers give. So I have 3, 1 here, and I have 4, 3 here. Subtracting these, 4, 3, minus 3, 1, gives 4 minus 3 is 1, 3 minus 1 is 2. So 1, 2, 1, 2. Well, this is not at all this vector, or is it? In fact, it is. As I told you, vectors have no location in space. They can be translated wherever you want. And the subtraction of two vectors gives another vector starting at the origin. That means what you can see here is it's indeed the vector that points from one tip to another tip, but it's moved to the origin of the coordinate space. But what you get if you subtract two vectors is really the difference between the two vectors, but moved. And that makes a lot of sense, of course, because now you can imagine adding A and C, B again. Okay, let's do this in Espresso too. I get one of these visualizers and start a new scene, paste it in here, create another vector B, and give it another color, and of course another location in space. And now let's subtract them. Well, it's a little bit long. 200 is better. And now I need a result. C. Another color, blue again. And an Espresso tag. A, B, and C. And we use the same math node again, but now we switch to data type vector, but the function we want to perform is subtract, and we subtract the vector, parameter vector of the A object and parameter vector of the B object, and feed them to the parameter vector of the C object. Let's do the color coding for readability. This could be easier, but well, A minus B gives the vector C. And indeed, if you have a close look, this vector is really the difference between these two locations if you move it. So let's do it. Let's move it just for visualization. What I can do, as you've seen in the addition result, I can move the whole generator around. So let's create an additional global coordinate port and take vector B, the orange one, and move the whole vector to this location. And now you have the correct setup. That means this vector here is a difference between these two. And now an interesting question appears, because the vector points from this vector to this vector. But couldn't it be the other way around? And the solution is very easy. It's about the order. The vector, the resulting vector of a subtraction operation always points to the tip that comes first. So it's tip first. Remember this. It's a rule. That means if I switch the operands, so let's create B minus A, I get the vector pointing in the different direction. And of course, to move it to the right location, I have to use the global position of A. And now I have the same result, but pointing in the other direction. Okay, that is vector subtraction. Very useful too. One example, what I can do with this is, for example, finding the location between two other locations or stuff like that. You need this really a lot. Or, for example, the target tag uses this concept. Because if you have two vectors, let's imagine this orange vector specifies the position of a target object and the green vector specifies the position of my object. By subtracting the two positions, I get the vector pointing from one to the other. And this vector is easily transferable into rotations, and then I have a target tag. Maybe we'll build this later. Okay, but as an introduction to vector math, one concept is still missing. So back to my drawing application and final concept, scaling vectors or multiplying vectors by a scalar. The first question that arises is, what the hell is a scalar? And a scalar is nothing but a number, a normal. So a real number, a floating point number. If you have a floating point number like 1.898, it's called a floating point number or a real number in math. But in the context of vector mathematics, we have to distinguish between vectors and normal numbers. And that's why we call everything that's not a vector a scalar. It's pronounced scalar. And why is this? You see in a second, because scalars are used to scale vectors, and that's why they are called scalars. So basically the operation is I have a vector 2, and let's call this vector A, and I want to multiply it by the number B. And B is 1/2, 0.5. So that means I have this vector A times B gives, and I have a vector quantity here indicated by this little arrow and a scalar quantity here indicated by the missing arrow, another vector. And this vector is really the same vector as before, only scaled. The length will be different. That means multiplying a vector by 0.5 gives the same vector as before with the same direction, but with half the length of the vector. That means this one here is a vector B. No, sorry, a vector C, which is our result. This portion here. And why is this? Let's do the algebra quickly. If you have a vector, let's say 2, 2, vector is called A, and you get A times 0.5. That means just multiply the both components 2 times 0.5. And that gives the half of 2 is 1 and half of 2 is 1. So the resulting vector is 1, 1. And what is this? This is 1, 1. And you see easily it's really half of that vector. And that means I can now not only chain translations together find the vector between two other vectors or move around in space, but I now can scale vectors. I can really make them longer or shorter, or even make them point in a different direction. Because if I multiply it with -1, 2.2 times -1, what I get is -2, -2, -2, -2, this vector here. So it's really the same vector with the same length, but pointing in a different direction. And this, it might pop out at you that this means that by scaling a vector, I can reach every point on this line, in this direction of the vector. I can make it longer and longer, shorter and shorter, and even switch direction. That means by scaling a vector, I can define the whole line. So basically, if I say this vector A here, times, not 0.5, but times z, for example, for z that lies between infinity and -infinity, that defines all points that lie on this line. Let's say you make a lot of calculations, and every time you increment z a little bit, it gives you this whole line. Okay. So far, for my first class, we learned 3 very important concepts of vector addition, vector subtraction, and scalar multiple of vectors. And in the next class, we will use all of these practically inside of Cinema 4D and get a little more complicated. I hope you enjoyed this class. I hope you had a little bit of fun. And if you have any questions, just ask at the forum. See you next week in the next class. Goodbye.